Betelgeuse is flickering. Right now, a star 900 times wider than our Sun is fading in your night sky, and no one knows exactly why. We're going to stand beneath its shoulder, watch a hidden companion stalk its surface, witness a shockwave already racing across space, and decode the whisper that says it may already be dead. If space and cosmic mysteries pull you in, tap that like button and subscribe so you never miss what we uncover next. Dim your lights, look up, we begin. Step outside on a cold, clear winter night and look southeast. There, stitched into the constellation Orion, sits a blood-orange spark that your eyes find before your brain catches up. That spark has a name: Betelgeuse, the shoulder of the hunter. For thousands of years, sailors used it to cross oceans. Farmers used it to mark the seasons. Ancient stargazers from Egypt to Australia painted it into their myths. It was reliable, it was steady, it was always there, until it wasn't. In late 2019, something impossible started happening in plain sight. Betelgeuse began to fade. Week by week, the red giant lost its glow, dropping to less than half its normal brightness. Astronomers who had stared at this star their entire careers suddenly could not recognize Orion. The hunter's shoulder looked wounded. Telephones started ringing across observatories from Chile to Hawaii. Astronomers who usually take weeks to respond to emails were answering within minutes. Something was wrong. Something big. And nobody had a confident answer. Here is what makes this terrifying. Betelgeuse is a supergiant in the final stages of its life. When a star this massive dies, it does not go quietly. It explodes. We call that explosion a supernova, and when Betelgeuse finally goes, it will be the closest one humans have ever seen in recorded history. Brighter than a full moon. Visible in broad daylight for weeks, casting shadows at midnight. And now it is dimming again. In late 2024, astronomers noticed the same pattern starting to repeat. A slow, strange fade. A flicker where there should be a steady flame. Only this time the scientific community is not laughing it off. Papers are being rushed. Observation time on the biggest telescopes on Earth is being cleared. Teams that never talk to each other are suddenly sharing notes. Because the last time Betelgeuse did this, we thought we understood it. We thought we had it figured out. We were wrong. Imagine watching a candle in a dark room. The flame dips, recovers, dips again. You assume it is a draft. You assume it is nothing. Then you realize there is no window. There is no door. And the candle is older than your grandfather's grandfather. Something inside the wax is changing, and you have no way to see what. That is where humanity stands right now with Betelgeuse. We are staring at a flame 640 light-years away, and we are watching it behave in ways our physics textbooks did not prepare us for. Some scientists believe we're seeing the final act before a cosmic explosion that will rewrite astronomy. Others think something is hiding behind the star, something we never detected before. A few whisper that Betelgeuse may have already exploded centuries ago, and the light carrying that news is still on its way to Earth. Every one of those possibilities is being taken seriously. Every one of them is backed by real data from real telescopes, and every one of them leads somewhere stranger than the last. Before we can understand why this dimming matters, we need to understand what Betelgeuse actually is. Because this is not an ordinary star, it is a monster, a dying monster, and the numbers behind it are about to make you uncomfortable. Picture our sun. Now picture swallowing the sun inside a sphere so vast that its outer edge would stretch past Mercury, past Venus, past Earth, past Mars, and keep going. That is Betelgeuse. If you dropped it into the center of our solar system, everything up to the asteroid belt would be inside the star. You, your house, your planet, all of it would simply cease to exist inside the churning layers of its atmosphere. Scientists estimate Betelgeuse is somewhere between 700 and 900 times wider than the Sun. The exact number keeps shifting, and that alone is a problem we will come back to. But even at the low end, the scale is almost impossible for a human brain to hold. A commercial jet flying at full speed around the Sun would complete the trip in about 6 months. Around Betelgeuse, the same jet would need more than 300 years, and yet despite being this enormous, Betelgeuse is shockingly light. Scientists call it a red supergiant, but supergiant describes the size, not the density. If you could reach into Betelgeuse and grab a handful of its outer layers, you would close your fist on almost nothing. Its atmosphere is thinner than the vacuum astronomers create inside laboratories on Earth. The star is less a ball of fire and more a swollen cloud, held together by gravity and fury. This is what happens when a massive star starts to die. In its youth, Betelgeuse was blue, hot, tight, compressed, probably around 20 times the mass of our Sun, burning through its hydrogen fuel at a rate our Sun could never match. Stars like this live fast. Our Sun has a lifespan of about 10 billion years. Betelgeuse will live less than 10 million. For a star, that is a blink. Now, after burning through hydrogen, then helium, then carbon, Betelgeuse has bloated outward like a balloon reaching its breaking point. Its core is compressing, its outer layers are cooling. The red colour you see in the sky is not warmth, it is exhaustion. The star is running out of things to burn, and each new fuel gets used up faster than the last. Here is the part that should stop you cold. When astronomers point their instruments at Betelgeuse, they see something nearly no other star does: a surface that moves. Giant cells of boiling plasma the size of entire planets rising and falling across its face. Imagine the surface of the ocean, but each wave is larger than Jupiter, and the foam is hotter than anything Earth has ever touched. Those boiling cells are not gentle. They launch enormous clouds of gas and dust into space, sometimes blocking light entirely. This is part of why Betelgeuse flickers. The star is shedding itself piece by piece, like a dying animal losing fur in clumps. And then there is the spin. Betelgeuse is rotating far faster than a star this old should be. Much faster. Suspiciously faster. Almost as if something spun it up, or is still spinning it. A hidden force we have not yet identified. That mystery has led to a theory astronomers never expected to consider, and it involves something lurking next to Betelgeuse that no telescope has ever clearly seen. The night of December 11th, 2019, an astronomer named Edward Guinan did something astronomers rarely do. He sounded a public alarm. Betelgeuse, the star he had tracked for more than 25 years, was dimming faster than anything he had ever recorded. His notes went from routine observations to urgent warnings in a matter of weeks. He published his measurements, and within days, the news spread across the astronomy community like wildfire. By February of 2020, Betelgeuse had dropped to about 1/3 of its usual brightness. Think about what that means. You are looking at the same star your ancestors looked at, and overnight, it was a different star. Photographs of Orion from early winter and late winter looked like two different constellations. The shoulder of the hunter had nearly vanished. Speculation exploded. Social media was flooded with claims that Betelgeuse was about to go supernova. News outlets ran frantic headlines asking if Earth was in danger. Some people genuinely believed they would wake up one morning and see a second sun in the sky. Even trained astronomers admitted they could not fully rule it out. Inside professional observatories, however, the mood was more careful. The drop was dramatic, yes, but it did not match the predicted signals of an imminent supernova. There were no detected neutrinos pouring from the star, no strange radiation bursts, no gravitational tremors. Whatever was happening, it was not the final collapse. So what was it? For months, scientists argued. Some suggested Betelgeuse was entering a long dormant cycle. Others proposed the star had cooled suddenly, like a fireplace where the biggest log has burned through and the flames dim before the next one catches. A third group believed the dimming was caused by something outside the star entirely. A cloud, a veil, a shadow. And this third theory would turn out to be closer to the truth than anyone expected. Then came the images. In January 2020, a team using the Very Large Telescope in Chile released a photograph that made people gasp. Betelgeuse, captured in high detail, looked lopsided, distorted. Its southern hemisphere was noticeably darker than the rest. The star was not dimming evenly. A specific region of its face had gone dark. This was the first real clue. Whatever was happening, it was not a global event. Something localized was dimming one part of the star, an eye closing, a bruise forming, a wound opening. You could look at the image and see that Betelgeuse was not just fading, it was hurting. By April 2020, this star began to recover. Its brightness slowly climbed back. By the end of the year, Betelgeuse looked almost like its old self, and most of the public forgot about it. Another space scare, another viral news cycle, move on. But the astronomers did not move on. They were now sitting on a mountain of data that needed to be explained. They had seen something rare, and they were determined to understand it. What followed was a 2-year investigation that would pull in infrared telescopes, space observatories, and ground stations across 4 continents. And the answer they pieced together was stranger than an early supernova. It involved a plume of gas, a sudden temperature drop, and a scar on the star that may still be healing today. Picture a volcano erupting sideways, not up into the sky, but outward across the land, throwing a wall of hot debris in one direction until everything behind it is swallowed in shadow. Now scale that up until the volcano is a star, and the debris is a cloud hundreds of times wider than Earth's orbit. That is the leading theory for what happened during the Great Dimming. In 2021, a research team combined years of data from space telescopes and came to a stunning conclusion. Months before the dimming began, Betelgeuse had coughed. A massive plume of hot gas had burst out of its southern hemisphere, punched through the star's own atmosphere, and drifted outward into space. As that plume moved away from the star, it cooled, and as it cooled, something remarkable happened. It condensed into dust, tiny grains, microscopic particles of heavier elements hanging in space like soot from a chimney. Billions of them, trillions, enough to form a vast dark veil drifting directly between Betelgeuse and Earth. The star had, in essence, spit out a shadow, and we were watching through it. This explains why the dimming was uneven. The plume did not cover all of Betelgeuse equally. It covered the southern hemisphere, exactly the region that appeared darkest in those famous photographs from the Very Large Telescope. It also explains why the dimming lasted only a few months. Once the dust drifted far enough away and spread out, the light from Betelgeuse could reach Earth again. But here is where it gets uncomfortable. Stars do not normally do this, at least not that we've ever watched in real time. Betelgeuse threw off an amount of material many times more massive than what our Sun sheds in decades, and it did it in one enormous belch. Scientists believe it released several times the mass of our Moon into space in a matter of months. Think about that. A cloud of dust with several lunar masses ejected by a single star burp. And we almost missed it. The question that followed was the one nobody wanted to ask. Why did this happen? What triggered it? One theory blames the boiling surface. Those planet-sized plasma cells we talked about earlier can sometimes rise with enormous force. If a massive cell surged upward at the wrong moment, it could have punched through the star's gravity and launched a plume into space. A freak event. Random. Possibly harmless. Another theory is darker. Some astronomers believe the plume came from deeper inside the star, not from the surface, but from somewhere below. A sign that Betelgeuse's internal structure is becoming unstable. A sign that the star is starting to tear at the seams as its core reshuffles itself in preparation for something much, much bigger. There is no way yet to tell which theory is correct. The dust has since dispersed. The scar, if it exists, is hidden beneath layers of boiling plasma. What remains is a mystery and a warning. Betelgeuse is capable of violence we did not expect. It can change its own brightness in our sky through acts of sudden volcanic release. And now something different is happening. Something the dust theory cannot explain. Because the new dimming does not match the old pattern. It is slower, deeper, stranger. And scientists are already whispering about a possibility that had never been seriously considered before. For more than a century, astronomers assumed Betelgeuse was alone, a solo supergiant drifting through space, radiating its cold red light without any partner. Every textbook showed it that way. Every model treated it that way. It was a lone wolf of a star, too massive and too unstable to share its orbit with anything. Then, in 2024, a team of astronomers released a paper that turned that assumption upside down. Hidden in years of brightness data from Betelgeuse, they found a pattern. A slow, repeating pulse. A rhythm that could not be explained by the star's own behaviour. Something was tugging on Betelgeuse. Something orbiting it. They nicknamed it Beetle Buddy. The idea is astonishing. Betelgeuse may not be alone after all. A smaller companion star, perhaps the size of our Sun or smaller, might be circling around it in a tight orbit. And every time this companion passes through Betelgeuse's outer atmosphere, it could be stirring up dust, blocking light, or even feeding off the supergiant's swollen layers like a shark in a whale carcass. If this is true, everything we thought we knew about Betelgeuse changes. Finding a companion to a supergiant is almost impossibly hard. Imagine trying to spot a firefly sitting next to a lighthouse. The lighthouse is so bright that your eyes adjust to its glare, and the firefly disappears into the background. That is exactly the problem astronomers face when searching for a small star hiding in the light of a red supergiant. The glare is so overwhelming that any orbiting companion would be drowned in brightness. But brightness is not the only tool astronomers have. They can measure tiny shifts in light, wobbles in position, pulses in wavelength. And when they looked at Betelgeuse through this finer lens, they saw the signature. A period of about 6 years where the supergiant's light rose and fell in a subtle, patterned way. This is called a long secondary period, and it has puzzled astronomers for decades. The simplest explanation is a companion. In 2024, an independent research team went further. They used the Hubble Space Telescope to hunt directly for the hidden star. They claimed a tentative detection. Then another team using different telescopes said they could not confirm it. A third team said, maybe. The debate is ongoing. The companion has not been definitively photographed, and it may never be. But the gravitational evidence continues to grow. If Beetle Buddy exists, it could be playing an active role in what we are seeing right now. Every time it passes close to Betelgeuse, it might disturb the supergiant's outer layers, triggering plumes of gas and dust to break free. It might even be accelerating Betelgeuse's death by pulling on its structure, like a child tugging at a fraying rope. Some astronomers have taken this one step further. They argue that Betelgeuse's strange spin, that suspiciously fast rotation we mentioned earlier, makes sense only if it once swallowed a companion star entirely. A smaller star, pulled in by gravity, spiraled into Betelgeuse and was absorbed. The leftover angular momentum is what spins the supergiant today. If this is true, Betelbuddy may actually be the second companion, a survivor, next in line. Standing on Earth, looking up at that red spark in Orion, you might not be seeing one star, you might be seeing two, locked in a dance that is slowly, violently ending. And then there is the other theory, the one that does not involve a companion at all, the one that says Betelgeuse is dying faster than any of us realized. Deep below the boiling plasma surface, below the thin outer atmosphere, below the turbulent layers we can see from Earth, Betelgeuse hides something we can never photograph. A furnace. A crushed, screaming core of unimaginable density where the laws of physics are being pushed to the edge. Inside our sun, hydrogen atoms crash into each other and fuse into helium. This releases energy, warms the star and keeps it alive. Our sun is nowhere near running out of hydrogen. It has about 5 billion years of this left. Betelgeuse is a different beast entirely. It used up its hydrogen long ago. Then it used its helium. Then it started burning carbon, the way older humans start burning fat after glucose runs out. Each new fuel burns faster than the last, and each one pushes the star closer to the edge. Astronomers believe Betelgeuse may currently be burning carbon, or possibly something heavier already. The exact stage is a matter of fierce debate. Carbon burning lasts only a few hundred years. If Betelgeuse has moved past carbon and is now burning neon, the star has only about a year of life left. If it is burning oxygen, only months. If it is burning silicon, the final stage, then the supernova could happen tomorrow, or tonight. Let that land for a moment. We do not know which stage Betelgeuse is in. We cannot see inside it. The thick outer layers block our view like clouds over a volcano. All we have are indirect clues, subtle hints in the light, whispers in the wavelengths, and the whispers are not comforting. Recent studies using advanced computer models suggest Betelgeuse may be much further along in its life than earlier estimates. Some researchers argue the star has already finished carbon burning. Others say it might be in the oxygen or neon phase right now. A few brave scientists have gone on record to say they would not be surprised to see Betelgeuse explode within the next decade. Not the next million years, the next 10. Here is what makes this especially wild. When a massive star approaches its final moments, it goes through rapid internal changes. The core temperature skyrockets. Heavier and heavier elements get forged in the inferno. Each fusion cycle lasts shorter and shorter times. Carbon burning lasts centuries. Neon burning lasts about a year. Oxygen burning lasts a few months. Silicon burning, the last gasp, lasts only 2 days. 2 days. That is the final countdown before a star like Betelgeuse collapses. 2 days between silicon burning and supernova. If you somehow had a detector that could see deep into Betelgeuse and catch the start of silicon burning, you would have exactly 2 days to prepare the world for the brightest night sky in human history. The problem is, we do not have that detector. Not yet. We cannot watch the core directly. All we can do is watch the outside and hope the outside gives us hints about the inside. And that is exactly what this new dimming might be. A hint. A signal from deep inside the star that something is changing. Not a plume this time. Something else. Something that suggests the furnace is behaving differently than it did 5 years ago. To understand why that matters, we need to talk about what a supernova actually does, and what it would look like from Earth. In the final half-second of Betelgeuse's life, something incomprehensible will happen. The core, after billions of fusions and countless collapses, will run out of fuel for the last time. It will no longer be able to resist its own gravity. It will fall inward on itself, crushing protons and electrons together so violently that they merge into something new, neutrons, packed together in a ball. This inward collapse takes less than a second. The outer layers of the star, still massive, still hot, still boiling, will not have time to react. They will suddenly find themselves with no core to push against. So they fall too. They crash down onto the new neutron core, hit it like a cosmic hammer and bounce. That bounce is the supernova. In the span of seconds, an explosion will release more energy than our sun will produce across its entire 10 billion year lifespan. More energy than every star in a small galaxy combined. Light, heat, radiation, matter, all of it expelled outward at a significant fraction of the speed of light. From Earth, this would not be subtle. Imagine standing outside on an ordinary evening, 640 light-years from Betelgeuse. The supernova has actually already happened from our perspective, because the light from the event will have been travelling toward us for centuries. But to us, on that evening, it is happening now. At first, nothing seems different. Then, somewhere in the direction of Orion, a point of light begins to grow. In minutes, it is brighter than any star in the sky. In hours, it rivals Venus. In a day, it outshines every celestial object except the moon. Within weeks, it is as bright as a full moon all by itself, casting shadows on the ground from a star at night. You would be able to read a book outside at midnight using only the light of the dying Betelgeuse. Car headlights would seem dim compared to it. People standing outside cities would see their own shadows stretching behind them in eerie, unmoving lines. For 3 to 6 months, Betelgeuse would be visible during the day, a second sun, hanging in the sky above Orion's shoulder, refusing to set. Birds would behave strangely. Their migration timing depends on sunlight. With a new light source in the night sky, confusion would spread. Nocturnal animals might alter their patterns. Tides would remain unchanged, but plant growth cycles might respond. For humans, it would be the most extraordinary astronomical event in recorded history. The last time a supernova this bright was seen was in the year 1054, when Chinese astronomers recorded a guest star so brilliant it shined for almost a month of daylight. Betelgeuse would blow that out of the water. But here is the thing people get wrong. The explosion itself would not hurt us. Betelgeuse is far enough away that the radiation and shockwave would not reach Earth with any damaging force. Our atmosphere would shield us from the energy. Life would continue as normal. The oceans would not boil. The ozone layer would survive. What would change is everything about how we look at the sky. Orion would lose its shoulder forever. The hunter would be forever wounded in our constellations, and in the place where Betelgeuse used to be, something new would remain. A glowing corpse, a neutron star, a scar, and that scar would carry secrets. After the supernova light fades, something remarkable will remain at the center of what used to be Betelgeuse, a neutron star. A ball of matter so densely packed that its properties defy everything we understand about ordinary physical objects. Picture taking the mass of our Sun and compressing it into a sphere about 12 miles across. 12 miles! Smaller than some American cities. That is a neutron star. And Betelgeuse, being more massive than our Sun, would leave behind a neutron star, or possibly something even stranger. The density of this object is almost impossible to describe with words alone. A single teaspoon of neutron star material would weigh more than every human on Earth combined. Not just a lot, billions of times more. The gravity at its surface would be over 200 billion times stronger than Earth's gravity. If you could somehow stand on one, you would not stand. You would be flattened into a film thinner than a single atom in less than the blink of an eye. Neutron stars spin fast. Some of them rotate hundreds of times per second, sweeping beams of radiation through space like cosmic lighthouses. We call these spinning neutron stars pulsars, and astronomers detect them by catching their rhythmic pulses as they flash past Earth. If Betelgeuse leaves behind a pulsar, it could become one of the brightest radio sources in our sky. But here is where it gets interesting. Betelgeuse might be massive enough to skip the neutron star stage entirely, and collapse into something even more extreme, a black hole. Scientists have debated this for years. The final mass of a dying star determines what it leaves behind. Below a certain limit, you get a neutron star. Above that limit, gravity wins the final fight and crushes the core past every known physical barrier. The result is a region of space where gravity is so strong that not even light can escape. A black hole in our cosmic neighborhood. This would be the closest black hole ever discovered by humans. Every other black hole we've detected has been thousands or millions of light years away. Betelgeuse's black hole, if it forms, would sit just 640 light years from Earth. Still impossibly far for human travel, but shockingly close by cosmic standards. It would become the nearest gravitational monster we know of, sitting silently in space where the red supergiant used to blaze. Whatever remains, the surrounding space will be transformed. The supernova explosion will throw debris outward at millions of miles per hour. This debris, rich in heavy elements forged during the star's final moments, will spread across interstellar space for thousands of years. Eventually it will cool, clump together, and form the building blocks of new stars and planets. The atoms in your body, the iron in your blood, the calcium in your bones, all came from ancient supernovae like this one. Betelgeuse will pay that same gift forward. Every element heavier than iron in the universe was forged in a supernova. Gold, uranium, platinum. All of it was cooked in a single second of stellar agony. When Betelgeuse goes, it will seed our corner of the galaxy with fresh heavy elements. Billions of years from now, new worlds might form from its ashes. And maybe, on one of those worlds, new life will look up at its own sky and wonder what came before. But before that distant future arrives, something much more urgent needs to be considered. The question nobody really wants to ask out loud. Here is a thought that keeps astronomers up at night. Betelgeuse is 640 light years away. That means the light we see from it right now left the star 640 years ago. Everything we see happening on Betelgeuse today is actually a snapshot from the past. We are watching medieval news, so when you look up at Orion tonight, you are not seeing Betelgeuse as it is. You are seeing Betelgeuse as it was during the final years of the Byzantine Empire, before the printing press, before the discovery of the Americas by Europeans, before your country's alphabet may have even existed in its current form. That light has been travelling for longer than modern civilization, which leads to a chilling possibility. What if Betelgeuse has already exploded? Somewhere in the last 600 years, the star could have gone supernova. The shockwave could be expanding, the radiation could be travelling outward, and the final flash of light could be somewhere along its journey toward us, crossing the cold dark of interstellar space, right now, at this moment, and we would have no way to know. Until the light arrives, Betelgeuse looks perfectly fine from our perspective. It continues to behave like a living star. It continues to dim and brighten. Every photograph we take, every spectrum we measure, every observation we make is describing a star that, in reality, may not exist anymore. If Betelgeuse exploded 300 years ago, we have about 340 years to wait before the light reaches us. If it exploded 100 years ago, only 540 years to wait. If it exploded just 50 years ago, we would have close to 6 centuries before anyone alive today sees the supernova. But there is another possibility. What if Betelgeuse exploded 639 years ago? What if the light is a single year away? What if the next time you read about something strange happening to Betelgeuse, it is because the light of its death is finally catching up to us? Some scientists have looked at the current dimming with exactly this framing. They cannot rule it out. They cannot confirm it either. But the timing is suspicious. Why is Betelgeuse suddenly showing such unusual behaviour? Why are 2 dramatic dimming events happening within 5 years? Why does the data keep revealing odd patterns that no supergiant has ever been caught doing before? One theory says these late-life changes are the signals we should expect in the final decades of a supergiant's existence. The boiling plasma grows more chaotic, the internal fusion cycles accelerate, the star essentially starts shaking before the collapse, and from Earth, we cannot tell if we're seeing signals from a star still alive or leftover echoes from a star that has already died. The first sign of a supernova in progress would not be light. It would be a ghostly, invisible wave of neutrinos. These subatomic particles are released by the trillions in the final collapse, and they travel nearly at the speed of light. Special detectors buried deep underground around the world are constantly watching for a sudden burst of neutrinos from Betelgeuse's direction. If those detectors ever light up, we will know, because the visible light will arrive just hours later, turning our night sky into something no human has witnessed in recorded history. The 2024 dimming does not match the 2019 dimming. That is the quiet sentence in new research papers that few people outside astronomy have noticed, and it is causing significant concern. In 2019, Betelgeuse dropped fast and hard. A cliff edge fade over a few months. Then it recovered. The dust plume theory explained it well. A chaotic but ultimately understandable event. This new one is different. Slower. Subtler. More like a long, steady bruise forming rather than a sudden punch. The brightness is wobbling in ways that do not match any of the previous models astronomers used to describe the star. When Betelgeuse was behaving normally, it had 3 known cycles of brightness change. A short cycle lasting about 185 days, a slightly longer cycle around 400 days, and the long secondary period around 6 years, which some scientists now attribute to the possible hidden companion star. The new dimming does not fit cleanly into any of these cycles. It is off rhythm, out of phase. Something in Betelgeuse has shifted, and the shift is not easy to dismiss. Some researchers suggest the star has entered a new instability phase. Its internal convection patterns may have reorganized. The boiling plasma cells on its surface may be behaving differently. Imagine if the ocean suddenly decided to have waves twice as tall as before, and nobody could explain why. That is what scientists are seeing on the face of Betelgeuse. Other researchers are more worried. They point to the fact that late-stage supergiants in the final decades before their supernova are predicted to show exactly this kind of change, a restructuring of how the star radiates, a wobble in its pulsation patterns, small hints that the internal fusion is changing its rhythm as each fuel runs out. There is no scientific consensus, and that in itself is unusual. Astronomy is a field where people are usually quick to rule things out, but with Betelgeuse, no one is ruling anything out. The conversations at conferences have shifted from confident declarations to careful admissions of uncertainty. One astronomer put it this way in a recent interview: "The star is teaching us that we did not understand supergiants as well as we thought we did. Every time we think we have Betelgeuse figured out, it does something new. Part of the problem is that we have never had this kind of ongoing, high-precision observation of a supergiant this close. Earlier generations of astronomers studied Betelgeuse with simple tools and broad averages. We now have space telescopes, infrared observatories, and interferometers powerful enough to image the surface of a star that far away. The level of detail we can see has exploded in the last decade, and the more we see, the less confident anyone is. Some scientists are using this new data to propose that Betelgeuse's internal structure is being disrupted by its hidden companion star. Every time Betelbuddy passes close, it perturbs the supergiant, stirring up material and changing the rhythm of brightness. If this is true, the current dimming might be a direct consequence of the companion's orbit. Other scientists are proposing something more unsettling: that the companion star is being pulled into Betelgeuse right now, in real time, slowly, over years, getting closer and closer, disturbing the supergiant more each time, and eventually the companion may be consumed. When a supergiant eats a companion, things happen that we have almost never observed before, and the results could accelerate the journey to supernova. In 2023, astronomers announced they had finally caught a star eating a planet in real time. Telescopes tracked the event as the star puffed up, swallowed its companion, and briefly flared before settling back down. It was a watershed moment. Humans had watched a cosmic meal happen from start to finish. Now imagine that same process, but instead of a planet, the meal is another star. When a supergiant like Betelgeuse swallows a smaller companion, the effect is violent. The companion does not simply disappear, it plunges deep into the supergiant's layers, releasing enormous amounts of energy as it falls. The companion star, still burning its own hydrogen, dumps itself into a larger sea of plasma. Gravity rips it apart, friction heats it up, angular momentum spins it around, and all of that energy has to go somewhere. The supergiant absorbs the energy and reacts. Scientists believe this is how Betelgeuse got its unusual rotation speed. At some point in its past, it almost certainly swallowed a companion. The angular momentum from the merger spun the supergiant up to speeds that are otherwise impossible for a star of its age and size. The evidence is in the numbers. A lone supergiant should not spin this fast. Betelgeuse does. If Betelgeuse once ate a companion, and if a second companion might still be orbiting, the same process could be happening again. Slowly, over thousands of years. The companion spirals inward, pulled by gravity, unable to resist. Eventually it gets too close. The outer atmosphere of Betelgeuse engulfs it. The companion starts to be stripped, heated, torn apart, and then, in a final plunge, it disappears into the supergiant. The aftermath of such an event could easily explain strange dimming behavior. a plunging companion would stir the outer layers of Betelgeuse into chaos. Plumes of dust could be launched outward. The star's brightness could fluctuate unpredictably. The core itself might be destabilized, pushed into a new regime of fusion as extra material is dumped into it. Some astronomers believe we may be witnessing the early stages of this exact process. The mysterious companion, if it exists, might be on its way in. Every close pass disturbs Betelgeuse a little more. The dimming events we are seeing could be the supergiant reacting to a stellar neighbour that is slowly, inevitably, falling into its embrace. This has implications for the supernova timeline. When a supergiant swallows a companion star, the added mass and energy can accelerate the dying process. Fusion cycles can speed up. The core can collapse sooner than it would have otherwise. A star that might have had another 100,000 years to live could instead explode in mere millennia, or sooner. The possibility that Betelgeuse is being influenced by a plunging companion right now is something scientists take seriously. Observations from 2024 and 2025 have been carefully analysed to see if the companion's orbit is decaying, if the period is shrinking, if the companion is getting closer with each pass. The data is noisy, the signal is faint, but the hints are there. If this theory is correct, we are watching a cosmic murder unfold in slow motion, a smaller star being slowly dragged to its death by a larger one, and in the process, accelerating the death of them both. And there is still one more piece of this puzzle that makes astronomers deeply uncomfortable. The actual timing of supergiant death is much less predictable than most textbooks admit. Ask a dozen astronomers when Betelgeuse will explode, and you will get a dozen different answers. Some will say 100,000 years, some will say 10,000. A few brave voices will say within a single human lifetime, and lately a handful have started whispering that it could happen in the next decade. The reason for this enormous range is simple. We cannot see inside the star. Everything we know about stellar death comes from computer models that simulate what should happen in the final stages of a supergiant's life. These models are based on physics, observations of other dying stars, and mathematical predictions. They are good, but they are not perfect, and Betelgeuse keeps breaking them. Each time scientists run new simulations with improved data, the estimated remaining lifespan changes. A study from 2023 suggested Betelgeuse might explode within 100,000 years. A study from 2024, using more refined models, shortened that estimate considerably. Newer studies in 2025 have started suggesting timelines measured in hundreds of years rather than thousands. Let that settle in. We're not talking about a change from 1,000,000 years to 900,000. We're talking about scientists reducing their estimates by orders of magnitude as the data improves. If this trend continues, the estimate could drop even further with the next round of observations. Some researchers have pointed out that this is what we should expect if Betelgeuse is truly in its final decades. The more we look, the more the numbers shrink. Because the closer a star is to death, the more obvious the signals become, and the signals are becoming more obvious. A team using one of the largest telescopes on Earth recently released a paper arguing that Betelgeuse's carbon-burning phase has already ended. If true, this would place the star in neon burning or beyond, dramatically shortening the window before collapse. Neon burning lasts only about 1 year. If Betelgeuse is in that phase right now, we are living through its final year. Other teams disagree. They argue Betelgeuse is still in carbon burning and has thousands of years left. The debate is unresolved and probably will not be resolved until the star actually explodes. What makes this especially strange is the psychological effect on scientists. Many astronomers admit privately that they do not want to predict a near-term supernova publicly. The reason is simple. If you predict the supernova will happen in 10 years and it does not, your reputation suffers. If you predict it will happen in 1,000,000 years and it happens in 10, your reputation also suffers, but differently. The safe prediction is always far in the future. Because of this, official estimates tend to be conservative. Astronomers say things like tens of thousands of years, because those numbers are unlikely to be proven wrong within a human lifetime. But the quiet whispers at conferences tell a different story. Some astronomers genuinely believe we could see Betelgeuse go supernova within the next few years. Nobody knows. That is the honest truth. The star is a ticking clock with a face we cannot read. It could tick for another 1,000,000 seconds or another 1,000,000 years, and we have no way to tell the difference until the final second arrives. And that final second will be announced by something small, something quiet, something that will arrive before the light does. A ghost wave of invisible particles that no normal eye can see. 2 hours before Betelgeuse's light reaches Earth, something else will arrive first. A silent flood of invisible particles, neutrinos, trillions of them, washing through your body, through the Earth, through every atom of matter in their path, without stopping, without colliding, without being noticed by anything except a few dedicated detectors buried deep underground. Neutrinos are the ghosts of the universe. They have almost no mass. They carry no electric charge. They pass through ordinary matter as if it were empty space. Every second, trillions of neutrinos from our own sun are passing through your body, and you feel absolutely nothing. You cannot block them with walls, with lead, with thousands of miles of solid Earth. They simply pass through. When a star goes supernova, an unimaginable number of neutrinos are released in the collapsing core. 99% of the energy of the explosion comes out as neutrinos. The visible light is a tiny afterthought by comparison. And because neutrinos barely interact with anything, they escape from the dying star almost instantly, while the visible light takes hours to fight its way out of the exploding layers. This means neutrinos arrive first, always. Deep under mountains and in old mines around the world, scientists have built massive detectors specifically to catch these ghostly particles. Japan has Super Kamiokande, a tank containing 50,000 tons of pure water, watched by thousands of sensitive light detectors. Antarctica has Ice Cube, a cubic kilometre of ice strung with thousands of optical sensors frozen into the continent itself. China, Italy, Canada and the United States all have their own systems. They are constantly watching. When a neutrino occasionally bumps into an atom inside one of these detectors, it creates a tiny flash of light. Scientists can see these flashes. Most of the time they come from the sun, or from cosmic radiation, or from distant sources. But if Betelgeuse explodes, the detectors will suddenly light up like never before, a sudden massive spike in neutrino activity, all coming from the same direction in space. This is where the supernova early warning system comes in. It is a network of neutrino detectors across the world that are programmed to automatically alert each other if any of them sees a sudden burst. If multiple detectors confirm the same signal at the same time, an emergency alert goes out to astronomers everywhere. Telescopes can be pointed, observations can begin, the world can prepare. And then, about 2 hours later, the light arrives. 2 hours. That is how much warning humanity would get. Not much, but enough to position every major telescope on Earth to watch the event unfold in real time, to set up spectrographs, to ready instruments across every wavelength, to broadcast the news. The last supernova close enough to produce detectable neutrinos was in 1987, in the nearby Large Magellanic Cloud. The neutrino burst arrived about 3 hours before the visible light, and it was a thrilling confirmation of every theory about how supernovae work. But that supernova was far, far more distant than Betelgeuse would be. The Betelgeuse neutrino burst, if it happens, would be vastly more intense. Instead of a handful of detections, we would see thousands, and those thousands of detections would tell us things we've never been able to measure before: properties of matter at extreme densities, behaviors of subatomic particles and conditions that cannot be recreated on Earth. It would be, without exaggeration, the most important astronomical event of the century, unless something weirder is happening first. Not every massive star ends with a brilliant supernova. Some do something stranger. They simply disappear. In 2015, astronomers confirmed something that had been theorized for decades but never directly observed. A massive supergiant in a distant galaxy, about 25 times the mass of our Sun, vanished without any explosion. 1 year it was there, glowing steadily in the night sky. The next year, it was gone. No supernova, no blast, no debris, just gone. The explanation is both mundane and terrifying. Some massive stars in their final moments collapse so completely that even the exploding outer layers cannot escape. Gravity wins the fight before the star has a chance to go supernova. The entire star, all of its mass, falls inward and disappears into a black hole, silently. Astronomers call this a failed supernova, and the possibility that Betelgeuse could experience one has been seriously discussed. Picture it. After millions of years of life, Betelgeuse reaches the moment of collapse. The core implodes, the outer layers begin to fall, but instead of bouncing off the core and rocketing outward as light and debris, they keep falling. The gravity of the new black hole is so strong that nothing escapes. No neutrinos, no light, no shockwave. The star simply fades from view as its matter is pulled into the singularity. If this happened to Betelgeuse, you would wake up one morning and find Orion missing a shoulder. No explosion, no bright night, just silence. The star would be gone, replaced by a black hole that you could not see at all. Astronomers would detect it only through the tiny distortions it would create in the light of background stars. Is this likely? Probably not. Most scientists believe Betelgeuse will explode in the traditional way, producing a bright supernova and leaving behind a neutron star or possibly a small black hole. But the failed supernova possibility cannot be entirely ruled out. Stellar mass models have uncertainties, and the exact outcome depends on things we cannot measure from the outside. A small fraction of massive stars are thought to end this way. Some estimates suggest as many as 1 in 5 die silently rather than explosively. If Betelgeuse is among that minority, we would witness one of the rarest astronomical events imaginable. A star vanishing from the sky. And we would have no cosmic fireworks, just a ghost where a sun used to be. The implications would be enormous. A black hole only 640 light-years from Earth would be incredibly valuable for science. It would be close enough to study in extraordinary detail. We could measure how it bends light from background stars. We could track its motion through space. We could learn things about black holes that distant examples never reveal. But it would also mean something else. It would mean that every supergiant out there carries this possibility. That the stars we see tonight could simply wink out tomorrow without any warning. That the universe is capable of stealing light without leaving a trace. Most scientists think Betelgeuse will put on a show. The neutrino detectors will light up. The sky will brighten. History will be made. but a small voice in the astronomy community still whispers about the alternative, the quiet death, the stealth collapse, the possibility that one of the most famous stars in human history could exit the stage without saying goodbye. Whatever happens, something even stranger has been hiding in the data about how Betelgeuse is changing its very shape. One of the most unsettling discoveries about Betelgeuse is something you would not expect to hear about a star. It is not round. Stars, by our natural intuition, should be spheres. They are made of gas held together by gravity. Gravity pulls equally in all directions, so stars should be balls. Perfect, glowing balls. Betelgeuse is not. When astronomers used the Hubble Space Telescope and the Very Large Telescope to image Betelgeuse in detail, they found something strange. The star has enormous bulges, pulsating regions that rise and fall across its surface over periods of months. Some of these bulges are larger than our entire solar system. They change the overall shape of the star in ways that should not be possible for something that massive. Imagine if Earth suddenly grew a mountain the size of a continent, and that mountain slowly pulsed up and down once a year. That is the kind of distortion happening on Betelgeuse, except on a scale beyond human comprehension. These bulges are caused by the boiling plasma cells we mentioned earlier. Each cell is a vast current of hot gas rising from the interior, reaching the surface, releasing its energy, and then falling back down to be reheated. On most stars, these convection cells are tiny, creating a fine sandy texture across the surface. On Betelgeuse, the cells are monstrous. 3 or 4 of them can cover nearly the entire visible face of the star. Each one is a planet-sized tower of plasma, rising and falling in a slow, terrifying rhythm. This creates a visible effect. Betelgeuse actually changes shape over time. Photographs taken years apart show different distortions, different bulges, different features. The star is never the same twice. It is constantly reshaping itself. And here is the unsettling part. Scientists believe these deformations may be getting worse. Recent studies suggest that Betelgeuse's outer layers have become more unstable over the past decade. The bulges are larger, the pulsations are more extreme, the convection cells are behaving with more violence than before. Every measurement shows a star that is becoming more chaotic as it ages. This is exactly what should happen if Betelgeuse is entering its final stages. As the core runs out of fuel and begins to restructure itself, the outer layers react by becoming more turbulent. The boundary between the core and the envelope becomes unstable. Energy flows outward in bursts rather than a steady stream. The surface boils more violently. In other words, the reason Betelgeuse does not look like a sphere anymore might be because it is struggling to hold itself together. There is a limit to how much deformation a star can sustain before something gives. If Betelgeuse loses enough material from its outer layers, or if the convection becomes extreme enough, the star could effectively start shedding itself. Huge clouds of gas and dust would drift away into space. The star would shrink and brighten unpredictably. The dimming we see today might be the beginning of this process, or it might not be. There is still enormous uncertainty. Stars like Betelgeuse are rare in our part of the galaxy, and we've only been studying this one in real time for a few decades. Everything we think we know could be wrong. Everything could be right. We are learning as we watch, and what we are watching is a star that refuses to sit still. A star that changes shape, rhythm, colour, and brightness in ways we're only beginning to understand. Because stars like this are not just dying, they are warning us. Every photon coming from Betelgeuse carries information. Not just brightness, but colour, motion, and chemistry. By breaking the light apart with instruments called spectrographs, scientists can read the fingerprints of what is happening inside the star, and those fingerprints have been shifting in ways that should not happen to a stable star. When light from a star passes through its own atmosphere, specific elements absorb specific wavelengths. This creates dark lines in the spectrum like barcodes. Each element leaves its own unique pattern. Hydrogen, helium, calcium, iron, titanium oxide. Each has its own signature. By measuring the positions and widths of these lines, scientists can determine the temperature, pressure, and motion of the gas producing the light. In Betelgeuse, those barcodes have been changing. Over the past decade, astronomers have noticed that certain spectral lines have shifted, widened, or weakened in ways that suggest major changes in the star's atmosphere. The amounts of certain elements appearing in the outer layers have fluctuated. The temperatures inferred from the lines have wobbled. The speeds of moving gas, which can be measured from tiny shifts in wavelength, have increased. This is not normal behavior for a stable supergiant. Stable stars have stable spectra. Their barcodes stay more or less the same from year to year. Only dying stars or stars in major transitions show this kind of variability. Some of the most dramatic changes involve something called the photosphere, which is essentially the outermost visible layer of the star. The photosphere of Betelgeuse has been expanding and contracting in ways that do not match any of the previously known pulsation cycles. At times, the star appears to be swelling outward. At other times, it seems to be contracting rapidly, pulling its surface closer to the core. One especially interesting finding involves the presence of molecules in the atmosphere. In 2021, astronomers detected unusually strong signals from titanium oxide in the upper layers of Betelgeuse. Titanium oxide forms only at certain temperatures, so its presence suggested that parts of the atmosphere were significantly cooler than expected. This was consistent with the cooling associated with the Great Dimming. But more recently, newer measurements have detected even stranger patterns. Hot and cold regions existing side by side in the atmosphere, separated by tiny distances. This shouldn't happen. It suggests that the energy inside Betelgeuse is no longer flowing smoothly from the core to the surface. Another signal involves magnetic activity. Stars generate magnetic fields through the motion of their internal plasma. These fields usually create subtle effects on the outer atmosphere. In Betelgeuse, the magnetic signals have been getting stronger and more erratic. Some scientists interpret this as evidence that the core is spinning up or becoming more turbulent. Others think it might be the effect of the hidden companion star, if it exists, interacting with Betelgeuse's fields. There is also the issue of ultraviolet light. When Betelgeuse was imaged in ultraviolet wavelengths in the 1990s, it showed certain patterns that researchers later used as baselines. Modern observations show those patterns have changed. The star is releasing ultraviolet radiation in different ways than before. The reasons are not fully understood. All of these shifts, when pieced together, paint a picture of a star undergoing profound change. Not collapse yet, not explosion yet, but something. Something that matches theoretical predictions of what a supergiant does in its final stretch. Something that suggests the countdown has started, even if we cannot read the exact number on the clock. And that clock might not just be measured in years. It might be measured in something we thought no one would see in their lifetime. There is something else moving outward from Betelgeuse, and it left the star thousands of years before any future supernova. A shockwave. A wall of compressed gas pushed ahead of the supergiant as it barrels through space. and if you looked at Betelgeuse with the right kind of telescope, you would see it. A bow wave, like a boat cutting through water. Betelgeuse is not stationary. It is moving through our galaxy at about 30 kilometers per second, which is roughly 67,000 miles per hour. As it travels, it pushes ahead of itself an enormous cloud of stellar wind, material constantly flowing off the star. This wind slams into the thin gas of interstellar space, creating a shock front that extends far ahead of Betelgeuse. Astronomers have photographed this shock front in ultraviolet as infrared light. The images are stunning. Betelgeuse sits inside a glowing cocoon of gas and dust that extends roughly 4 light-years outward in the direction of its motion. That cocoon is hotter, denser, and more active than the surrounding galactic space. It is essentially a cosmic wake, and the wake has structure. It has knots and filaments. It has regions where dust has collected in dense pockets. It has what astronomers describe as ancient stellar burps, material that Betelgeuse coughed out tens of thousands of years ago and which is still drifting around the star in thick clumps. This is where it gets interesting. When Betelgeuse finally explodes, the supernova blast will slam into this cocoon. The explosion shockwave will plough through the gas and dust already there, creating a magnificent second wave of light and radiation as the materials crash into each other. This phase could last for years or even decades after the initial supernova, producing a slowly evolving nebula visible to future generations. But there is an even stranger possibility. Some of the material in the cocoon is thought to have come from earlier mass loss events, possibly from previous eruptions of Betelgeuse itself, possibly from interactions with the hidden companion star. And that material might contain hints about Betelgeuse's past that we have not fully decoded yet. Scientists have started mapping the shape of the cocoon in extraordinary detail. In doing so, they have found patterns that suggest Betelgeuse has undergone multiple episodes of violent mass loss over the past 100,000 years. Each episode left behind a shell of material. The cocoon is not smooth. It is layered, like the rings of an onion, with each layer telling the story of a different moment in the supergiant's life. And the outermost layers, the oldest ones, are now reaching the edge of the cocoon and merging with the interstellar medium. Eventually, all of this material will continue outward, spreading across space, mixing with the gas that forms new stars. Some of it will travel for millions of years. Some of it will be incorporated into future planets. Some of it perhaps will one day be breathed by creatures on worlds that do not yet exist. If you could fast forward time and watch Betelgeuse explode from far outside the galaxy, you would see a brilliant flash, then a slowly expanding cloud of debris, then the cloud crashing into the older cocoon, lighting up the surrounding space, and eventually everything fading as the new materials spread into the wider galactic neighborhood. But before any of that happens, something has to trigger the final collapse, and the trigger might already be inside the star, hidden in a layer of burning elements we have never directly observed. Cut open a dying supergiant, and you would find something remarkable. A structure like an onion. Layer after layer of different fuels, each one hotter and heavier than the layer above it, each one burning the ashes of the layer before, each one a stage of the star's long, desperate fight against gravity. On the outside is hydrogen, what little remains after billions of years of burning. Below that is a shell of helium, left over from when the star's core converted hydrogen into helium during its main sequence life. Below the helium is a layer of carbon. Below the carbon, oxygen and neon. Below those, silicon. And at the very heart, if the star has reached its final stage, is a dense, screaming core of iron. Each layer is fusing, each layer is producing its own energy. The star is essentially run in multiple burning cycles simultaneously, stacked one on top of the other, all working to keep it alive a little longer. The inner layers burn hotter and faster than the outer ones. Hydrogen fusion is slow and efficient. Carbon fusion is much faster. Oxygen fusion is faster still. Silicon fusion, the last stage, is so rapid that a star can exhaust a supply of silicon in about 2 days. 2 days! That is the final breath of a supergiant. What makes this structure terrifying is that each new fuel produces less net energy than the last. Hydrogen to helium releases the most energy. Each subsequent fusion releases progressively less. By the time a star is fusing silicon into iron, the returns are almost nothing, and when the core becomes pure iron, fusion stops delivering energy altogether. Iron absorbs energy rather than releasing it. The star's support system fails. That is when gravity wins. The moment iron accumulates in sufficient quantities, the core can no longer hold itself up. It collapses in less than a second, and everything above it comes crashing down. Here is why this matters for Betelgeuse right now. Depending on what fuel it is burning, we have radically different predictions for how much time is left. If Betelgeuse is still in carbon burning, we have thousands of years. If it is in neon burning, we have about 1 year. If it is in oxygen burning, we have months. If it is in silicon burning, we have 2 days, and we cannot tell which layer is active. The outer atmosphere of Betelgeuse, which is all we can observe, gives only indirect clues. Elements leaking through to the surface are one signal. Changes in brightness cycles are another. Shifts in magnetic activity might be a third. Scientists are trying to piece together which burning stage the core is in using these clues. The answers so far are inconsistent. Some recent models place Betelgeuse in the oxygen burning stage. Others argue it must still be in carbon. The disagreement is not just about a small number, it is about orders of magnitude of remaining life. And none of the models can be verified without either a supernova happening or much more advanced observations that we do not yet have. Here is a chilling thought. If Betelgeuse is currently in silicon burning, then by the time you finish listening to this video, the star might be in the final moments before collapse. Not literally, of course, but in stellar terms the window is unimaginably narrow, and we have no way of knowing whether it is happening right now. That uncertainty is why astronomers cannot stop watching. Every telescope pointed at Betelgeuse is essentially a guard standing at the door of history. Imagine waking up one morning, stepping outside, and noticing something different about the sky. It is bright, far too bright for morning. You look up, and there, where Orion should be, is a light so intense you cannot look directly at it. A second sun, not as warm as the first, but visible in full daylight, hanging in the southern sky like a wound in the heavens. This is what the first day of a Betelgeuse supernova would look like. The moment the light arrives, Betelgeuse would begin to brighten rapidly. Over a matter of hours, it would climb through every stage of brilliance, first matching Venus, then surpassing it, then climbing past every other star in the sky. Within a day or so, it would reach peak brightness, possibly shining as brilliantly as the full moon, but concentrated into a single point of light. For several weeks, this supernova would be visible during the day, a point of light so bright that even the glare of the sun could not wash it out. Airplane pilots would notice it. Commuters driving to work would glance at the morning sky and see a star staring back. Children would ask questions that no one knows how to answer yet. At night, the effects would be transformative. The Betelgeuse supernova would be bright enough to cast shadows, real, sharp shadows. You would stand outside in a rural field, facing away from cities, and see your own silhouette stretched behind you by starlight. This has not happened in human history. Not in any recorded era. Animals would notice. Nocturnal hunters, which rely on darkness to catch prey, would have their nights disturbed for months. Migratory birds, which navigate partly by stars, could be confused by the sudden appearance of a new bright source. Insects might flock toward the unprecedented brightness. Fish in shallow waters might alter their feeding patterns. Human culture would also transform. Imagine what it would mean for religions, mythologies, art and science fiction. A second sun in the sky. A bright, unmoving star visible day and night. Films would be made about it. Books would be written. Songs would try to capture the strange feeling of looking up at something impossible. Astronomy as a field would change permanently. The event would be observed in wavelengths we can barely measure today. Every neutrino detector, every gamma-ray telescope, every infrared and ultraviolet instrument would be focused on this one point in space. Scientists would gather more data in the first 48 hours than they have collected from all previous supernovae combined. Nobel Prizes would be awarded for discoveries nobody has made yet, and then, slowly, over months and years, Betelgeuse would fade. The peak brilliance would drop. The visible in daylight phase would end. By year 2, the former star would be just a bright dot in the sky. By year 10, fainter still. Eventually, nothing would be visible to the naked eye, but telescopes would continue to watch the expanding nebula for centuries. Orion would never be the same. The constellation we have known for thousands of years, the hunter with his 3-star belt and his bright shoulder, would lose its defining feature. Textbooks would have to be rewritten. Star maps would become historical documents. Generations after the event would grow up looking at a version of Orion we never saw. And everyone alive during the event would remember. The way your grandparents remember where they were when famous historical moments happened. You would remember where you were the night Orion lost its shoulder, but there is an even rarer possibility nobody likes to discuss. What if Betelgeuse is not the only star preparing to die? Betelgeuse is not the only massive star in our cosmic neighborhood that could go supernova. It is just the most famous. Scattered across the night sky are several other red supergiants, each one a potential candidate for stellar death. And astronomers are keeping an eye on all of them. Antares, the bright red heart of the constellation Scorpius, is one of them. Roughly the same type of star as Betelgeuse. Similar size, similar age, similar fate awaiting it. Antares is about 550 light-years from Earth, roughly as close as Betelgeuse. When Antares eventually dies, it will produce another dramatic supernova visible from our planet. The timing is unclear. Maybe it happens tomorrow, maybe in 1,000,000 years. No one knows. Then there is VY Canis Majoris, often called one of the largest known stars in the universe. It sits about 3,800 light-years away, far enough that its supernova would be less dramatic from our view than Betelgeuse. But VY Canis Majoris is so massive and so unstable that scientists consider it a strong candidate for a failed supernova. The kind where the star silently collapses into a black hole without exploding. Rigel, the brilliant blue star at Orion's foot, is also a potential supernova candidate, though blue supergiants have different evolution paths than red ones. Rigel is larger and hotter than Betelgeuse, but on a separate timeline for death. The point is this: supernova events in our cosmic vicinity are not as rare as they might sound. Over a few thousand years, several of these massive stars are likely to end their lives. Betelgeuse is just the one that has captured our attention right now, And here is something you might not realize. Our neighborhood is relatively quiet compared to other regions of the galaxy. In the core of the Milky Way, near the supermassive black hole at the center, supergiants come and go more rapidly. The density of young, massive stars is higher there, but those stars are tens of thousands of light years from Earth. Their supernovae are too distant to be as dramatic for us. What Betelgeuse offers is proximity. If it explodes, we will get a close view. We will measure things we cannot measure at longer distances. We will see details that would normally be smeared out by the vast distances between us and other supernovae. There is also the historical angle to consider. Earth has witnessed nearby supernova before. In the year 1054, Chinese astronomers recorded a guest star in the constellation Taurus that became so bright it was visible in daylight for nearly a month. That star was about 6,500 light-years away. We now know it as the Crab Nebula, the expanding remnant of that ancient explosion. In the year 1572, Danish astronomer Tycho Brahe observed another bright supernova in Cassiopeia. It became one of the most important astronomical events of the Renaissance and contributed to the scientific revolution. In 1604, another supernova appeared, this one studied carefully by Johannes Kepler. Since Kepler's supernova, no naked-eye supernova has been observed within our own galaxy. That is more than 400 years without a front-row seat to a stellar death. We are due for another one, and Betelgeuse may be the one that finally delivers. But what happens if multiple supergiants go off close together in time? That is a scenario worth considering, because the aftermath of a nearby supernova has more consequences than just a bright light. A common reassurance from astronomers about Betelgeuse's eventual supernova is that Earth is safe. This star is far enough away that the blast will not harm us. The visible light will be beautiful but non-threatening. Life will continue. This is mostly true, but it is not the whole story. When a supernova explodes, it releases an enormous amount of energy across many wavelengths. Visible light is only a small fraction. There's also ultraviolet radiation, X-rays, gamma rays, and cosmic rays, which are high-energy particles that travel at near light speed. All of these are sent outward from the explosion, and all of them can affect nearby planets, including Earth. For a supernova to be truly dangerous to Earth, scientists estimate it would need to occur within about 30 light-years of us. That is much closer than Betelgeuse. At 640 light-years, Betelgeuse's radiation will be significantly diluted by the enormous distance. Most of the dangerous effects will be absorbed or deflected before they reach our atmosphere. Mostly. Cosmic rays are an exception. These high-energy particles are not confined to the direction of the initial blast. They can spiral through galactic magnetic fields, eventually reaching many different regions of space, including Earth. A nearby supernova can increase the cosmic ray flux hitting our planet for thousands of years after the event. This is not enough to sterilize the planet or kill its inhabitants, but it can have subtle effects. One potential effect is on the ozone layer. Cosmic rays and gamma rays can break apart molecules in the upper atmosphere, including the ozone that shields us from harmful solar ultraviolet radiation. A reduction in the ozone layer, even a small one, could lead to increased ultraviolet exposure at ground level. This could affect plants, animals, and humans in various ways over long timescales. Another effect is on the climate. Increased cosmic ray activity has been linked to cloud formation in the lower atmosphere. More clouds could mean more reflected sunlight and cooler temperatures. This is speculative and debated. but a few scientists have suggested that past supernovae might have contributed to historical climate changes on Earth. There is also the possibility of electronic interference. If a nearby supernova produces a strong burst of gamma rays or electromagnetic radiation, satellites in orbit could be affected, power grids could experience surges, communication systems could be disrupted. None of this would be catastrophic for a supernova at Betelgeuse's distance, but some temporary effects are possible. Now here is where it gets interesting. Scientists have studied ancient rock and ice cores on Earth to look for evidence of past supernovae, and they have found it. Layers of iron isotopes deposited in ocean sediments suggest that a supernova occurred within a few hundred light-years of Earth about 2 to 3 million years ago. The iron came from the exploded star and rained down on Earth's surface over thousands of years. There is also evidence of a second supernova a bit more recently. These ancient explosions did not wipe out life, but they did deposit measurable radioactive material in our planet's geology. If Betelgeuse explodes, we should expect a similar long-term deposition of heavy elements from its debris cloud. Over tens of thousands of years, some of that material will reach Earth's atmosphere and eventually settle into the oceans and the ground. Future geologists, if humanity exists in that far future, will be able to read the Betelgeuse layer in the rock record the same way we read past supernovae today. But there is one more danger that is often overlooked, and it involves something we have almost no defense against. In the weeks following the supernova, everything will focus on the light, the incredible brightness, the night sky transformation, the historic photographs. But in the background, something more subtle will begin to happen, something we will not notice at first. The supernova debris, a vast expanding cloud of hot gas and heavy elements, will start to race outward. This cloud is made of everything the star once was: the hydrogen from its atmosphere, the helium from its middle layers, the carbon, oxygen, silicon and iron from its deep interior, plus heavier elements forged during the explosion itself, like gold, platinum and uranium, all of it mixed together, heated to millions of degrees and thrown outward at speeds approaching 10,000 miles per second. At first, this cloud will be too hot to form any solid matter. The temperatures are too extreme for atoms to bond, but as the cloud expands, it will cool, and as it cools, atoms will start to combine, molecules will form. Eventually dust grains will appear, tiny microscopic specks of heavy elements frozen out of the expanding gas. This is called supernova dust, and it is one of the most important sources of heavy elements in the universe. Within a few years, the dust production will be massive. Entire solar systems worth of material will condense into fine particles drifting outward in the expanding supernova remnant. This dust will glow in infrared light for decades. Telescopes will watch it grow and change, filling in details about how matter behaves under extreme conditions. Over thousands of years, the dust will mix with the gas already present in interstellar space. It will spread across vast regions. Some of it will travel outward in the direction of our solar system, slowly approaching Earth as it rides the currents of the galactic medium. Eventually, some of the atoms from Betelgeuse's explosion will reach our atmosphere, mingle with the air we breathe, and settle onto the ground we walk on. This is not a fast process. It could take tens or hundreds of thousands of years for noticeable amounts of supernova material to reach Earth. By then, humanity may be very different from today, but the connection will be real. Future generations on Earth, if they exist, will quite literally have Betelgeuse in their bones. here is a beautiful thought that I want you to hold for a moment. Every heavy element on Earth came from an ancient supernova. The calcium in your skeleton, the iron in your blood, the zinc in your skin, the phosphorus in your DNA, all of it was forged in stars that died long before Earth was born. When you look at Betelgeuse tonight, you're looking at a star that will continue the same cycle. Its death will seed new generations of stars and worlds with the ingredients for life. The universe, in a sense, is constantly recycling itself. Stars are born, they burn, they die, and their ashes become the raw material for the next generation. We're living in a particular moment of this cycle, able to witness a supergiant near the end of its life. Within a few 100,000 years, the debris from Betelgeuse will have spread so widely that it will be impossible to trace it back to a single origin. But right now, we can still identify Betelgeuse as the future source of that cosmic seeding. So in a strange way, Betelgeuse's death is not just an ending, it is also a beginning. The beginning of something new that will unfold over timescales longer than any human civilization has ever existed. But before that new beginning, there is still the matter of what exactly sets off the final collapse, and it may be stranger than we imagined. Iron is the element that ends stars. Deep inside a dying supergiant, iron accumulates in the core as the final product of fusion. Once iron builds up in sufficient quantity, the star's death becomes inevitable. Because iron, unlike every other element a star burns, does not release energy when it fuses with anything. It absorbs energy. This is the cruel twist at the heart of stellar evolution. All throughout a star's life, fusion produces energy. That energy pushes outward, holding the star up against its own gravity. But when the core turns to iron, the energy production stops. Fusion attempts require energy input rather than releasing it. The core has no way to maintain its internal pressure, and gravity does not wait. The moment iron accumulates to a critical mass, the core collapses, not slowly, not gradually. In a fraction of a second, the entire inner region of the star falls inward under its own weight. Protons and electrons are crushed together into neutrons. The core becomes a tiny, incredibly dense ball, and everything above it suddenly has nothing to push against. This is the trigger of the supernova, an iron core collapse. For Betelgeuse, this trigger has probably not happened yet. If it had, we would have seen the neutrinos and light already. But every second that Betelgeuse continues to exist brings it closer to this moment. Every second, more iron is accumulating in its core. Every second, the fuel for fusion is being exhausted. Every second, the star is one breath closer to its final breath. Scientists cannot measure iron accumulation directly. The inner core is hidden from view, but they can measure other things that hint at the process: temperature, spin, brightness, chemistry. And when all of these are combined, a picture emerges of how close Betelgeuse might be to the iron core stage. The picture is blurry, but not reassuring. Some recent research suggests that Betelgeuse's core might be a good deal more massive than earlier models suggested. A larger core means iron will accumulate faster. A faster accumulation means a shorter remaining life. If these newer models are correct, Betelgeuse could reach the iron core stage much sooner than traditional estimates suggest. Other research pushes back. The models are complicated, and small changes in assumptions lead to big changes in predictions. One team might estimate 50,000 years, another might estimate 500, a third might say 5,000. All of them are using legitimate physics. All of them are disagreeing about the same star. What everyone agrees on is this: once iron core collapse begins, everything happens fast. The collapse itself takes less than a second. The bounce follows immediately. The shockwave that becomes the supernova begins within a few seconds of that. By the time humans on Earth notice anything, the dramatic events inside Betelgeuse have already finished. The light and neutrinos we see are echoes of something that happened in an instant. This is a strange realization. When Betelgeuse finally explodes, the actual collapse will be so fast that no telescope could possibly capture it. The outer fireworks will last for months, but the core event, the iron collapse itself, will be over before a single camera could photograph it. We will see the aftermath. We will never see the moment, and yet we can already detect hints of what is brewing deep inside the star, because even now, before the final collapse, Betelgeuse is not entirely silent about its condition. It is whispering. Stars make sound. Not the kind we can hear with our ears because there is no air in space to carry acoustic waves to Earth, but inside a star, where hot plasma churns and flows, pressure waves travel through the material. These waves behave like sound. They create oscillations, vibrations, and resonances in the body of the star. Astronomers have figured out how to listen to these stellar sounds indirectly. By carefully measuring tiny changes in a star's brightness and surface motion, they can detect the internal pulsations. This field is called astroseismology. It is essentially a form of stellar eavesdropping, and Betelgeuse has something important to say. Recent astroseismic studies have detected patterns in Betelgeuse's brightness and pulsation that suggest its internal oscillations are changing. The rhythms are shifting, the frequencies are drifting, new modes are appearing, old modes are fading. It is as if the star is humming a different song than it did a decade ago. These changes are interpreted by scientists as evidence that the internal structure of Betelgeuse is evolving. The layers are rearranging. The boundaries between fusion zones are shifting. The dynamics of hot plasma flowing from the core to the surface are transforming. All of this is consistent with the star that is moving through its final evolutionary stages. Think of it this way. If you listen to a violin being played, you could tell a lot about the instrument just from the sound. A perfectly tuned violin produces one set of tones. A damaged or detuned violin produces different ones. A violin whose strings are about to break makes different sounds again. By listening carefully, you could diagnose the condition of the instrument without ever seeing it. Betelgeuse's sounds are telling us that the instrument is not in tune anymore. It is damaged, it is under stress, and it may be close to breaking. One especially intriguing finding involves a phenomenon called mode beating. This is where two different oscillation frequencies within a star interfere with each other, producing slow patterns of brightness change. Betelgeuse's mode beating has shifted in recent years. The patterns have become more erratic. New beats have appeared that were not present before. Some scientists believe this is a sign that the internal temperature distribution of the star is changing, a classic marker of advanced evolutionary stages. There's also something strange happening to the length of Betelgeuse's natural pulsation cycles. The 400-day cycle, which has been one of the most reliable features of the star's brightness for over a century, has started to show variations. The timing is not as precise as before. Some cycles are longer, some are shorter. The clock is losing accuracy. For a dying star, this is meaningful. The natural pulsations of a stable supergiant are set by its physical properties, especially the relationship between its core, its envelope, and its surface. When those properties change, the pulsation changes. and Betelgeuse's pulsations are changing. Scientists cannot tell from these sounds exactly when the supernova will happen. The mode changes are subtle, the shifts are slow, but they are consistent with what theoretical models predict for the final stages of a red supergiant's life. If these predictions are accurate, Betelgeuse is now past the midpoint of its final evolutionary chapter, not at the beginning, possibly near the end. Not all astronomers interpret the data this way. Some argue the changes are natural variations that happen in any supergiant over time. Others argue they are strongly suggestive of imminent collapse. The truth is, we do not have enough historical data on supergiants to know for certain what these signals mean. We're essentially reading a book we've never read before, in a language we're still learning. 5 years after the Great Dimming of 2019, scientists found themselves in an unusual position. They had built up an enormous body of knowledge about how Betelgeuse behaves. They had documented its patterns. They had explained the strange 2020 dip. They had developed models to predict what a dimming event would look like in the future. And then the 2024 dimming started, and the models failed. The new event did not follow the patterns of the old one. It was slower, more spread out, more ambiguous. It did not match the dust plume signature. It did not match the expected cycles. It did not match anything scientists had built their models around. At first, some researchers dismissed this as a minor variation. Betelgeuse is a complex star. It does unusual things. One new dip, even if it did not fit the models, might not mean anything bigger. Just wait and see. But as the dimming continued into 2025, waiting and seeing became more uncomfortable. The star was not behaving like anything in the scientific literature. Observations from multiple telescopes confirmed that the brightness decline was real and sustained. It was not a photographic error. It was not a measurement artifact. Betelgeuse was genuinely entering a new phase of dimming, and nobody had a solid explanation. This was the moment when concern began to creep into the scientific community. Not panic, not headlines, but quiet, careful concern expressed at conferences and in private conversations. The kind of concern that comes when the data does not match any of your predictions. A major review paper was published explaining the differences between the two dimming events. The authors noted that while the Great Dimming of 2019 was explained by a dust plume, the 2024 event showed no clear dust signature. There was no corresponding cloud. There was no corresponding temperature change. There was no matching asymmetry in the star's surface. The star was just getting dimmer, uniformly, for reasons the data could not explain. One possibility raised by the authors was that the dimming reflected an internal change in the star's structure, a change in the energy output from the core, a reshuffling of how fusion was distributing energy through the layers. If true, this would be significant because it would mean Betelgeuse was approaching some kind of transition in its life cycle. Another possibility involved the hypothetical companion star. If Betelbuddy is real and is currently on a close pass of Betelgeuse, it could be causing complex disturbances in the supergiant's outer layers. These disturbances might not produce a visible dust cloud, but they could affect the star's overall brightness in subtle ways. This hypothesis requires the companion to be passing through a region of the orbit where it interacts heavily with Betelgeuse's atmosphere. A third possibility, held quietly by some researchers, was that the dimming represented an early sign of approaching supernova. Stars nearing the end of their lives are predicted to show erratic brightness patterns. They might dim and brighten unpredictably. They might alter their pulsation rhythms. They might do things that have never been observed before because we have never had the tools to watch a star this close right before it explodes. If this third possibility is correct, then Betelgeuse is essentially in its death throes. Not immediate, not this year or next year, but within a timescale that is much shorter than the thousands of years traditional estimates suggest. The problem is there is no way to tell which of these three possibilities is correct. The data is consistent with all of them, and astronomers are now entering a period of intense observation, trying to gather more signals that might disambiguate the theories. The stakes of this disambiguation are bigger than most people realize. The challenge of studying Betelgeuse is fundamentally a challenge of resolution. At 640 light-years, even this enormous star is only a tiny pinprick of light in our sky. To see its surface features, to measure its shape, to track changes in real time, we need telescopes with extraordinary precision. For most of history, this was impossible. Traditional telescopes could not resolve the disk of any star other than the Sun. All stars appeared as points. You could measure how bright they were, but you could not see their faces. That changed in the last few decades with the development of interferometry. Interferometry combines the light from multiple telescopes to create the equivalent resolution of one giant telescope. The bigger the spacing between telescopes, the better the resolution. Using this technique, astronomers can now see the surfaces of nearby giant stars. They can spot the boiling plasma cells. They can track bulges and bumps. They can measure shape changes over months and years. Betelgeuse is one of the favorite targets. Its size and proximity make it an ideal candidate for high-resolution imaging, and every new generation of interferometers has revealed more detail than the last. There is a catch. Resolving Betelgeuse requires complex coordination between multiple observatories. The instruments must be perfectly aligned. The atmosphere must cooperate. The weather must be clear. The data must be processed carefully. This is not easy. New instruments are coming online that will significantly improve our view of Betelgeuse. The European Extremely Large Telescope, currently being built in Chile, will have a main mirror almost 130 feet across when it's completed. When combined with adaptive optics, it will be able to image Betelgeuse's surface in unprecedented detail. The James Webb Space Telescope, already operating, has infrared capabilities that let it see through dust clouds and track changes in the star's outer atmosphere. Space-based missions are also being planned. There are proposals for dedicated supergiant monitoring telescopes that would continuously observe Betelgeuse and a few other candidates like Antares. These would produce uninterrupted data streams, catching transient events that ground-based telescopes might miss. Even more exciting is the development of improved neutrino detectors. The current generation of detectors is impressive, but could be improved significantly. A new generation of detectors currently being built in different countries would be able to catch more neutrinos and localize them better. If Betelgeuse goes supernova, these next-generation detectors could identify the star's direction within seconds, not minutes. Gravitational wave detectors are another piece of the puzzle. When a massive star collapses, it produces gravitational waves. These waves are incredibly faint, but with sufficiently sensitive detectors, they could be picked up from a nearby supernova. Current gravitational wave observatories are not sensitive enough to catch Betelgeuse's signature at this distance, but upgrades planned for the coming decade should change that. Put all of this together and the picture is clear. We're approaching a point where we will have extraordinary tools to study the next nearby supernova. If Betelgeuse explodes within the next decade, we will capture it in ways no previous event has been captured. The data will be unprecedented, the scientific value will be immense. The question is whether Betelgeuse will cooperate with our schedule, whether it will explode in time for our best instruments to be ready, whether it will wait another 100,000 years, by which point our descendants will have even better tools to study it, or whether it will go tomorrow, catching us with our current generation of instruments, which are impressive but imperfect. We are in a race, and we do not know how much time is left on the clock. On December the 12th, 2023, something very special happened to Betelgeuse. An asteroid named Leona passed directly between the star and Earth, briefly blocking its light. This kind of event, called an occultation, is extraordinarily rare. The alignment between the asteroid, the star, and our planet has to be nearly perfect. For Betelgeuse, occultations happen only once every few hundred years for any given observer. The event lasted only about 12 seconds. But in those 12 seconds, scientists learned things they could not have learned any other way. When an asteroid passes in front of a star, it blocks the star's light in a very specific pattern. By carefully measuring how the light dims and recovers, scientists can deduce the shape and size of the star. This is because an asteroid is much smaller than a star at interstellar distances, meaning it acts like a small shadow passing across a large bright surface. The dimming pattern reveals the outline of the surface. Observers across Europe and the United States captured the event from multiple locations. Each location saw a slightly different part of the star being blocked by Leona as the asteroid moved. By combining all of these observations, scientists could reconstruct the shape of Betelgeuse with unprecedented precision, and the results were surprising. Betelgeuse appeared even more distorted than previous images had suggested. It was not a simple sphere. It was not even a simple oval. Its outline had bumps, dips, and irregular features. The star was genuinely misshapen, with large regions of differing brightness and visible bulges across its surface. The occultation also provided the most accurate measurement of Betelgeuse's angular size to date. This is the measurement of how wide the star appears to us in the sky. Combined with distance estimates, this gave scientists a much better estimate of Betelgeuse's actual physical size. The results aligned with estimates in the 700 to 900 solar diameter range, though significant uncertainty remained. One of the most intriguing findings from the occultation was the discovery of an apparent brightness gradient across the star's surface. The center of Betelgeuse's disk was noticeably brighter than the edges, a phenomenon called limb darkening. This is expected for most stars, but the specific pattern in Betelgeuse was different from what standard models predicted. The darkening was less pronounced than expected, suggesting that the outer atmosphere might be extending further than previously thought. If Betelgeuse's atmosphere is larger than models suggest, this could mean the star is already losing mass through its outer layers at an accelerated rate. It could also mean that the boundary between the star and space is less clearly defined than we imagined. This has implications for how we model stellar evolution and how we interpret brightness changes. The occultation also provided clues about the presence of the hypothetical companion star. If Betelbuddy exists and is passing near Betelgeuse, it might have been visible during the occultation as a tiny additional dimming event. Some observers reported seeing anomalies in their data that could be consistent with a small companion, but the evidence was not definitive. Future occultations of Betelgeuse will not be common. The next similar event may not occur for decades or even centuries, so the Leona occultation represented a once-in-a-lifetime opportunity for scientists to study this particular dying star. Every piece of data from that 12-second event is being analysed and reanalyzed. New papers are being published based on different aspects of the measurements. What the occultation confirmed, beyond any doubt, is that Betelgeuse is a far stranger object than our textbooks describe. It is distorted, it is unstable, it is changing, and it continues to challenge every assumption scientists make about how supergiants behave. Betelgeuse is not just losing mass through occasional dust plumes. It is continuously shedding material. Every second, streams of gas flow outward from its surface into space. Over the course of a year, Betelgeuse releases enough material to equal roughly 1/10 the mass of Earth. Over thousands of years, this adds up to enormous amounts of matter being dispersed into the interstellar medium. And this material is unusual. When scientists analyze the light from Betelgeuse's outflow, they see a rich cocktail of heavy elements: silicon, iron, titanium, magnesium, aluminum, sometimes even gold and other precious metals in trace amounts. These heavy elements were forged over the star's lifetime through successive fusion cycles. Now they are leaking into space, seeding the galaxy with raw materials for future stars and planets. The outflow is not uniform. Different parts of the star lose material at different rates, and the direction of the outflow can vary over time. This is partly because of the boiling plasma cells, which launch gas upward from specific regions. It is also because of magnetic activity, which can channel material along magnetic field lines. And it may also be because of the hypothetical companion, which could be stripping material from Betelgeuse during close orbital passes. As the material moves outward from Betelgeuse, it cools. At different distances from the star, different chemistry happens. Close to the surface, the material is still hot enough to remain largely gaseous. Further out, it cools enough for molecules to form. Even further out, dust grains condense. Far away, the dust and gas merge with the interstellar medium and become part of the slow cosmic recycling process. Scientists have mapped the outflow from Betelgeuse in great detail using infrared observations. The maps show complex structures with density variations and irregular shapes. Some regions of the outflow are denser than others. Some show signs of shockwaves, where material moving at different speeds has collided and compressed. One particularly interesting finding is the discovery of silicon monoxide clouds in Betelgeuse's atmosphere. These molecules form in specific temperature conditions and serve as markers for certain layers in the star's outer envelope. By tracking the distribution of silicon monoxide, scientists can map the temperature structure of Betelgeuse's outflow. Recent observations have detected changes in the silicon monoxide distribution. Regions that used to have strong signatures now have weaker ones. New regions have shown up with unexpected patterns. The chemistry of Betelgeuse's atmosphere is actively changing on timescales that scientists can measure over years. This chemical evolution is significant because it tells us about the physical processes inside the star. If the chemistry is changing, it means the temperatures and pressures that drive that chemistry are changing. Those conditions are set by what is happening deeper in the star. So indirectly, we're getting information about Betelgeuse's core through the chemical fingerprints of its outflow. One theory about the current dimming event is that it is connected to changes in the outflow. If Betelgeuse is releasing more dust than usual, or if the composition of the dust has shifted, this could affect how light from the star reaches us. Complex dust clouds could absorb and scatter light in ways that cause subtle dimming over extended periods. Unlike the 2019 event, which involved a single large plume, the current event might involve a more gradual increase in dust production across multiple regions. This theory is consistent with some observations, but not others. Scientists are continuing to gather data, and they are paying special attention to the chemical composition of the material currently flowing from the star. If new elements appear in the outflow, or if existing elements change their abundances, It could indicate major internal changes happening in Betelgeuse right now, and some of those changes might connect to an idea that sounds closer to science fiction than science. If Betelgeuse's supernova leaves behind a neutron star, and if that neutron star is spinning fast enough and oriented the right way toward Earth, we could end up with something spectacular. A pulsar. A cosmic lighthouse flashing at us from just 640 light-years away. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space. If a beam happens to cross our line of sight, we see a regular pulse of radiation, like a lighthouse beam flashing across a dark ocean. The pulses can range from seconds to milliseconds, depending on how fast the neutron star spins. A Betelgeuse pulsar would be remarkable for several reasons. First, it would be the closest pulsar to Earth by a huge margin. Currently, the closest known pulsars are hundreds or thousands of light-years away. A Betelgeuse pulsar at 640 light-years would be a front-row seat to one of the most extreme objects in the universe. Second, it would provide an unprecedented laboratory for studying extreme physics. The conditions inside a neutron star are beyond anything we can reproduce on Earth. Densities greater than atomic nuclei. Magnetic fields a trillion times stronger than any produced in laboratories. Rotation rates of hundreds of times per second. All of these things could be studied in detail with a nearby pulsar. Third, and maybe most exciting, a Betelgeuse pulsar could be used to test fundamental physics. The precise timing of pulsar pulses is so regular that they serve as cosmic clocks. By monitoring a nearby pulsar for long periods, scientists can detect tiny variations caused by gravitational waves, changes in space-time, and other exotic phenomena. Having such a clock close to Earth would enable experiments that are currently impossible. Whether Betelgeuse actually produces a pulsar depends on several factors. Most neutron stars form with some rotation, but the specific rotation rate is difficult to predict in advance. It depends on the angular momentum of the collapsing core, which is hard to measure from the outside. It also depends on whether magnetic fields are preserved during the collapse and how strong they end up being. If Betelgeuse's current rapid rotation is preserved in some form through the collapse, the resulting neutron star could rotate very quickly at first, producing a very fast pulsar. Over time, it would slow down as it loses energy to the pulses it emits, but in its youth, it could be one of the most impressive pulsars ever observed. Not every neutron star becomes a pulsar visible from Earth. The beams have to be pointed in the right direction. If the beams miss our line of sight, we would still have a neutron star at Betelgeuse's location, but we would not see regular pulses. We could still detect the star through other means, such as its thermal radiation and its gravitational effects on nearby matter. There is also the possibility that Betelgeuse's collapse produces something stranger than a typical neutron star. Recent theoretical work has explored the possibility of exotic stellar remnants. Quark stars, for example, a hypothetical object where the matter is so compressed that it breaks down into its fundamental particles. Magnetars are neutron stars with magnetic fields so strong that they produce spectacular bursts of radiation. Any of these could result from Betelgeuse's death, depending on the specific conditions of the collapse. Whatever forms, it will be special, a permanent monument to the star that died, a remnant we can study for as long as humans exist, something that represents the end of Betelgeuse and the beginning of whatever comes next at that point in space. And when that remnant finally exists, it will mark a before and after. A cosmic clock that divides the age when Betelgeuse was a red dot in Orion from the age when it became something else entirely. One of the most remarkable aspects of a nearby supernova is its universality. Everyone on the nighttime side of Earth would see it. Not just astronomers, not just scientists, everyone. Every person with working eyes and an open sky would look up and see the same thing at the same time. A dying star, bright enough to cast shadows, hanging in the constellation Orion. This would be one of the largest shared human experiences in history. Consider what it would mean. Roughly 4 billion people live in the northern hemisphere where Orion is visible during winter months. During Betelgeuse's bright phase, most of them would be able to see the supernova personally. Children in rural villages, elderly people in city apartments, students in libraries who look up from their books, construction workers taking their lunch breaks, everyone. Previous major astronomical events have been impressive but not truly universal. Solar eclipses are visible only along narrow paths. Comets are visible mostly in dark rural skies. Meteor showers are spectacular but require specific viewing conditions. Even the brightest supernovae of the past were visible for weeks, but they did not match the intensity of what Betelgeuse would produce. Betelgeuse's supernova would be something different, so bright that light pollution from cities would not wash it out, so long-lasting that everyone would have multiple opportunities to see it, so dramatic that even people who normally do not look at the sky would be drawn outside to stare at it. The psychological and cultural effects would be profound. People would talk about it. News networks would cover it constantly. Schools would dedicate class time to teaching about it. Religious leaders would address it in sermons. Artists would capture it in paintings, songs, poems, and films. It would become a defining moment of whatever era it occurs in. For astronomers, it would be overwhelming. Every observatory in the world would be flooded with requests for time on their instruments. Every university with an astronomy program would see massive surges in applications. Every science journal would be packed with submissions about Betelgeuse. The field would never be the same. There would also be philosophical implications. Seeing a star die in real time, knowing that you are watching the end of something that existed for millions of years, would give people a new perspective on the universe and our place in it. For a brief time, everyone on Earth would be reminded that they are connected to the larger cosmos, that our tiny planet exists within a vast and active universe where stars live and die. Some cultures throughout history have viewed supernovae as omens, good or bad depending on the tradition. Modern societies would likely generate their own interpretations. Conspiracy theories would spread. Religious movements might arise or dissolve. Entire new belief systems could emerge from the event. Scientists, of course, would try to shape public understanding. They would emphasize that the supernova is a natural event, that it poses no danger to Earth, and that it represents an amazing opportunity to learn about the universe. Most people would accept this explanation. Some would not. There would also be practical considerations. Observatories in remote areas would become tourist destinations. Astronomy courses would see enrollment spikes. Science journalism would thrive. Telescope manufacturers would struggle to meet demand. Through all of this, the supernova would continue to unfold in the sky, brightening at first, then slowly fading, changing colour as different elements in the expanding debris emit different wavelengths. Over months and years, it would transform from a brilliant point of light into a slowly expanding nebula. And through all of those changes, humans would watch together, sharing a moment unlike anything our species has experienced before. It would be a milestone, a before and after. Like few events in human history, one of the hardest things to accept about astronomy is how slow most things happen. Human lives are short. The universe is old. On the timescale of the cosmos, a human lifetime is barely a blink. Most cosmic events take thousands or millions of years to unfold. We rarely get to see them happen, which makes Betelgeuse special. Because for the first time in recorded history, we might actually get to witness one of the most dramatic events in the universe. Not read about it in textbooks, not see it in simulations, actually see it with our own eyes. But there is also an unsettling side to this. We do not know when. We could be weeks away. We could be centuries away. We could be hundreds of thousands of years away. Every night, billions of people around the world look up at Betelgeuse. And every night they might be looking at a star that has just exploded, or a star that is about to, or a star that will continue to burn for longer than any civilization that has ever existed. There is a strange peace in this uncertainty, a kind of cosmic reminder of how little we control. We've built remarkable tools. We've advanced our science incredibly. We've learned so much about the universe, and yet, when it comes to the actual timing of a nearby stellar death, we are still guessing. The star itself refuses to tell us its own plans. This quiet is deceptive. Look up at Betelgeuse tonight, and it will seem like just another red point of light. A pretty shoulder in the constellation Orion. You would never know from a casual glance that this star is one of the most unusual objects in our cosmic neighborhood, that it is actively dying, that it has a possible hidden companion, that its surface is boiling in ways no other star we study boils, that its light is 640 years old, that the next chapter of its life could begin any moment. Some people find this thought uncomfortable. The idea that something so dramatic could happen without warning is unsettling. Most humans prefer predictability. We like schedules. We like to know when important events will happen. Betelgeuse does not care about our preferences. It will do what it does when it does it, and we will simply have to adapt. Other people find this thought exhilarating. The knowledge that we could be witnesses to one of the most important astronomical events in human history is thrilling. It means that every night we look at Betelgeuse, we are potentially participating in something meaningful. Even if tonight is just another ordinary night, the possibility remains, and that possibility itself is a kind of cosmic gift. For astronomers, Betelgeuse has become an obsession. Every new observation is a chance to gather more data. Every new paper is a chance to contribute to our understanding. Every new tool is a chance to see the star more clearly. The scientific community has rallied around Betelgeuse in ways that rarely happen with other objects. And through all of this, Betelgeuse itself is indifferent. It does not know that humans exist. It does not know that our telescopes are pointed at it. It does not know that we have named it, mythologized it, studied it, and argued about it for thousands of years. It just burns. It just shines. It just continues its own slow, inevitable process of evolution toward whatever comes next. That indifference is its own kind of beauty, a reminder that the universe does not exist for us. We exist within it. We witness what we can. We understand what we can. And sometimes, rarely, we get lucky enough to see something truly extraordinary. Betelgeuse may be about to give us one of those moments. They're a possibility we have not discussed much. A possibility that sits in the background of every serious conversation about Betelgeuse. The possibility that everything we think we know about this star could be wrong. We do not have a perfect track record with stellar predictions. Supergiants are rare. The ones near us are few. The ones we can study in detail are fewer still. Our models are built on limited data, and the conclusions we draw from them carry significant uncertainty. When astronomers say Betelgeuse will explode within 100,000 years, they're making an educated guess based on incomplete information. The actual answer could be very different. What if Betelgeuse is much younger than we think? What if its unusual rotation and strange behaviour are signs of something other than aging? What if the Great Dimming was not a sign of a dying star, but a sign of something entirely new that we've never seen before? What if the 2024 dimming is part of a natural pattern that happens every few decades, but which we simply have not observed long enough to recognise? These are not crazy questions. Scientists ask them seriously. Because the history of astronomy is full of examples where the common interpretation turned out to be wrong. For instance, pulsars were initially misidentified as possible alien signals. The first discovered pulsar was nicknamed LGM-1, standing for Little Green Men, because its regular pulses seemed too artificial to be natural. Only after more pulsars were discovered did scientists realize these were a new type of stellar object. Our understanding of pulsars has since been revised multiple times. Similar stories exist for black holes, quasars, gamma-ray bursts, and many other cosmic phenomena. Each time a new type of object was discovered, it took years or decades to understand what it really was. Our current interpretations of these objects have evolved dramatically from the initial explanations. Could Betelgeuse be in a similar position? Could we be fundamentally misinterpreting what we see? Some dissenting voices in the astronomy community have argued yes. They point out that we have only been observing Betelgeuse in detail for a few decades. They note that our supergiant models are based on very few actual observations. They suggest that the behaviour we are seeing might represent a completely new class of stellar phenomenon that does not fit into existing categories of stellar evolution. One alternative theory is that Betelgeuse is not as close to death as we think. Its unusual behaviour could be the result of a long-term cycle that lasts tens of thousands of years, which we're only catching a glimpse of during our brief period of detailed observation. If true, Betelgeuse might continue its current dance for much longer than the short timelines some researchers suggest. Another alternative is that the hypothetical companion star is playing a larger role than expected. If Betelbuddy is real, it might be driving much of the observed behaviour. The dimming events, the rotation speed, the shape distortions, all of these could be consequences of the companion's influence, rather than signs of approaching death. If the companion leaves or stabilizes, Betelgeuse might return to more ordinary behaviour. Yet another possibility is that Betelgeuse has encountered some kind of interstellar disturbance, a region of unusual gas density, a small cloud that has interacted with the star's outer atmosphere. Something external rather than internal could be driving the recent changes. Each of these alternatives has some supporting evidence and some counter-evidence. None of them can be ruled out entirely, and each of them would mean that the timeline to supernova is much longer than some researchers currently suggest. The honest answer is that we do not know which interpretation is correct. We will not know until we gather more data, and even then we may still be wrong. The universe has a way of surprising us, and Betelgeuse seems particularly eager to defy simple explanations. Somewhere in space, right now, photons are moving. They're travelling at the speed of light. They carry information about Betelgeuse that we have not yet received. Some of those photons will arrive tonight. Some will arrive tomorrow. Some will arrive in 1,000 years. Each one is a message in a bottle, launched from a star 640 years ago, slowly making its way across the dark ocean of space to finally wash up on the shore of our planet. We're always looking at Betelgeuse's past. We cannot help it. Light takes time to travel. Everything we see is old news. The star we observed tonight is showing us what was happening during the medieval era. Wars were being fought, empires were rising and falling, the Black Death was sweeping across continents, and the light from Betelgeuse was just beginning its journey toward our eyes. 640 years from now, some future person will look up at the sky and see what Betelgeuse is doing right now. Tonight, this moment. They will see the current dimming as ancient history, long past. They will wonder, just as we wonder, what was happening in their current era to the star they see. This is the nature of cosmic communication. Everything is delayed. Everything is partial. Everything is, in some sense, fiction from the moment the light leaves its source. And yet, we try. We build telescopes. We point them at stars. We catch photons. We decode the messages. We piece together stories. Every fact we have about Betelgeuse came from a photon that spent centuries travelling through empty space before ending its journey in a detector somewhere on Earth. Every theory we have was built from these ancient messages. Every prediction we make about the future is built from observations of the distant past. This is why Betelgeuse matters so much, not just because it is a dying star, not just because it is beautiful, not just because it might explode in our lifetimes. It matters because it represents the deepest form of cosmic connection. It is far enough away that everything about it is history, but close enough that the history feels current. It is a bridge between the immense scale of the universe and the tiny scale of our human lives. When Betelgeuse finally explodes, whenever that happens, the photons carrying the news will begin their journey to us. They will travel through interstellar dust clouds. They will pass through the magnetic fields of nearby stars. They will ride the curvature of space-time. They will spread outward in all directions, a spherical wave of information about a star that is no longer alive. Some of those photons will hit Earth, some will hit the eyes of people who happen to be looking up at the right moment. Some will be caught by telescopes and analysed. Some will miss us entirely and continue outward forever, carrying the news to other worlds that may or may not exist. And the neutrinos will arrive first. Ghost particles unseen, flooding through Earth, through everything, silent and invisible hours before the light, announcing to whatever detectors are watching that a star has died. Until then, we wait, we watch. We hope our telescopes are pointed in the right direction. We hope our neutrino detectors are operating. We hope our tools are capable of capturing what needs to be captured, and we live our ordinary lives. We go to work, we have dinner, we sleep, we wake up, we do it again, and every now and then, if the night is clear, we look up. We see that red spark in Orion. We remember that it is dying, that it may already be gone, that it could transform the night sky any moment. The light we see tonight is a gift from the past. The light we will see in the future is a gift still travelling, and somewhere between the past and the future, a star is preparing to give us a moment our species will never forget.